Yaskawa.
Good morning, everybody. This is Nishant Unikrishnan. I'm a motion application engineer with the motion division at Yaskawa. Welcome to the Rotary Knife Solution Package with MPIEC Controllers webinar. The topic for today will be split up into these subdivisions. Basically, I would like to explain the different types of rotary knives that we've encountered in our experience with motion products. With and without registration of the two broad classifications. We will touch on the functionality of a rotary knife application solution that can take care of applications that require registration and those that do not require registration. We will show you a automatic cam generation function block that will create regular cams that can help in your rotary knife application, and then the rotary knife function blocks themselves that will take care of your solution. And finally, we will show you how to implement the function blocks in your application to get your solution that you desire. We'll start off with the first kind, the rotary knife applications that do not require registration. As you can see here, there's a knife, and in this example, in this pictorial example I have, there is just one blade. You could have configurations where you may have multiple blades as well, and this solution will take care of applications that require multiple blades as well. So in this example that I've shown here, there is one blade which is held at the 180-degree position on a 0 to 360 full rotation of one circle. The cutting area is defined as 0 degrees or 360 degrees, as you may see it. There is a small window that represents the synchronized speed where the knife has to match the linear speed of the products that are being processed. The important parameters that a user needs to look at when they are designing a linear or a rotary knife are the circumference of the whole system, the circumference of the knife itself. There is a cut angle that is involved, which is basically the synchronization angle, which translates to a linear distance on the product. The number of blades is important, and also the part length is important here. As you can see, those are the parameters that I have highlighted in my slide here. So these are the main parameters that drive the rotary knife application, and these are some of the parameters that the user has to take care of to understand and completely use in the application solution. The other type of rotary knife solution that we will be talking about is rotary knife application with registration, and that means you have a sensor and you have some product lengths or some registration marks on the product which determine where the part has to be cut or processed. And basically the sensor could be placed close to the knife or relatively far away from the knife, depending on the machine. Here again, the important parameters that the user should keep in mind are the circumference of the knife, the cut angle or the angle where speed synchronization should be achieved, the number of blades, and the nominal part length. Now, the applications with registration typically have two subdivisions within itself. There are applications that have part lengths that are known, but they may have small variations, positive or negative variations. So let's say you think the nominal part length is 10 inches, you could have variations greater than 10 or less than 10, could be 9.9 or 10.1. So you may have small variations in your product length. There's also another type of registration-based rotary knife where you may have randomly coming parts that come in at unknown intervals. That also falls in this category of rotary knife with registration. Now, I keep mentioning rotary knife. This can also be used in applications where you have a rotary placer or a rotary picker or any kind of rotary axis that processes parts as it comes through. That can be taken care of with this solution method. So this template that we are presenting and offering today consists of 3 different function blocks, mainly. And these 3 different function blocks are shown below. The first one is a rotary knife cam generator. The second one is a rotary knife without registration, and the third one is rotary knife with registration. So these are the 3 main function blocks. Like I said before, the main parameters that need to go into your rotary knife application are the number of blades, the part length, the angle, synchronization angle or cut angles, and the knife diameter. Now, once you pass these parameters into the rotary knife cam generator function block, that function block uses the cam generator function block inside it and creates 3 cam tables. It creates a ramp in cam table, a running cam table, and a ramp out cam table. And these cam tables are basically used to ensure that your rotary knife application can do your application, do the cutting or the processing in as smooth as a profile as possible, which is why we have the ramp in and the ramp out that accompany the running cam tables. So this is for smooth ramp in, starting from 0 velocity to your speed matching velocity, and also for a smooth ramp out from your running cam table. Once these 3 cam tables are created, you could use any one of these 2 function blocks at the bottom. One thing to note is that the rotary knife cam generator function block needs to be used in a slow task, because this is a static process. It just is creating creating 3 cam tables, so you do not have to run it in a fast task. The data that is created by the cam generator is fed into the 2 function blocks shown below, rotary knife with or without registration, and those 2 function blocks can be run or need to be run at a fast task. And you can see once the ramp in, running, and ramp out cam blocks are fed into one or the other of these 2 function blocks, you basically get your required functionality. And we'll talk about this in detail. The first function block is the rotary knife cam generator function block. This block is essentially used to generate your ramp in, running, and ramp out cam tables. Now, when you look at the running cam table, only if the part length is equal to the circumference of the knife will you have a straight line relation between the master, which could be a conveyor or your product on which your encoder is running, and the slave axis, which is the servo. So if the part length is equal to the knife's circumference, you get a straight line or linear relation between the 2. The parts shown in yellow at the 2 ends are the speed matching areas here. And that's typically not the case in every scenario. You generally do not have a fixed part length. You make a machine with variable part lengths, or a machine that can process parts of variable lengths. And if your part length is greater than the knife circumference, this is the profile that you want to be able to get, where after the speed match, you want your knife to slow down in the middle of the master cycle. This is the slowing down area, and once it's done with the slowing down and it's ready to match in speed again, it accelerates and matches speed with the master profile. The other case is if your part length is less than the circumference of your knife. In this case, you basically have to make sure that the slave axis accelerates before it matches speed. So these are the 3 different cases, or 3 different kinds of running cam profiles that need to be generated for general rotary knife applications. Apart from just creating the running cam table, the rotary knife cam generator function block also creates ramp in and ramp out cam tables based on the parameters that are entered. And these cam tables have to be created such that they blend together easily and smoothly. You can see that the ramp in profile has to blend with the running profile, and it has to merge with the ramp out profile as well. Again, looking at the speed match areas in the in the three cam tables, you have your ramp in cam profile, the running cam profile, and the ramp out cam profile. There are two speed match or two cut zones that I'm showing in this particular example here. An important aspect in setting up your rotary knife is the home position or the start position for your rotary knife. In the case of a one knife application, this solution expects the user to set the single knife at 180 degree position as shown here, where the home position is 180 and the speed match or cut area is the 0 degree position in your cycle. And this is to accommodate an easy ramp in. As you can see here, from the home position of 180, the knife can basically come down and cut at the 0 degree area, which is right here, and then continue running if need be. And if there is a request to ramp out, it can basically go from the 0 position to the 180 degree position as smooth as possible, as the ramp out cam profile dictates. If you have two knives, as shown below, the home position would be such that you are set, the two knives are away from each other, and they are basically set in the orientation shown here with the two knives here. And the home position would be 90 degrees, and the cut position would be 0 again. If you have three knives, this would be the home position with the bottom one showing the cut position and the top picture showing the home position. And with four knives, the orientation is going to be as shown here, where the home position is at 45 degrees and the cut position is at 0 degrees. Now, this is very critical. It's very important that the user understands these home positions before a rotary knife application is implemented. Here is the new function block that we're introducing. It's called Rotary Knife CamGen, and let's explain the various parameters that need to go into this function block to get what we want. The top two variables, knife parameters and blend data, are elements that are generated by this function block for use in other parts of this template. So the user does not really have to fill in any of this data. The user will have to define these variables. The first one, knife parameters, is a new data type called rotary knife structure, and the blend data is something that those of you who've used the CAM toolbox, CAM blend function block have seen before. Blend data is a variable that is created as a blend struct data type. So the user has to define these variables, but does not have to define or initialize any of the elements of these two data types, because these are created in this function block. The user will have to provide the part length that is going to be used, the diameter of the knife, the number of knives, the start angle for speed matching, and the end angle for speed matching. This reversible cam input will be discussed later. So as you can see here in this one knife example, your home position is 180 degrees with the knife facing away from where the product is going to be cut or placed. 350 degrees is the start of the speed match area. 0 degrees is where the speed is exactly matched, and 10 degrees is where the speed match ends. After that, the knife basically goes back to its 180 degree position. So once the cams have been generated, this is the rotary knife function block without registration. And as you can see here, some of the parameters are variables that were created by the rotary knife CamGen function block. This is the blend data that was created, which has the cam table IDs of the ramp in, running, and ramp out cams. Knife parameters has some of the parameters that will be used inside this function block, and this one is created by the rotary knife CamGen function block as well. The user in this case will have to decide on the logic when to execute your rotary knife, or when to execute your ramp in and when to execute the ramp out for this particular application. And you can see here is one example where where the user executes a ramp in, and in the very next master cycle, the ramp in is done where the axis goes, in the case of a one knife system, it goes from 180 to 360 or 0 degrees, makes a cut, and then runs along and makes another cut here. And then at this point, in this master cycle, if a ramp out was executed, at the very next cycle, a ramp out is done and the knife goes back to its 180-degree home position and stays there. Here are some real examples that we got from our application examples that we tried on our rotary knife demo. This is an example where we just have a single product where you just make one cut. So you ramp in, cut, and you ramp out. And you can see here that the ramp in was executed in this master cycle. In the very next master cycle, the slave starts its ramp in process. It's a smooth ramp in process. You can see from the velocity that it started off from a 0 velocity and accelerated. Now, although it accelerated, it did not have to, it basically had to come down or reduce its velocity so that it could match the master's velocity. As you can see here, the velocity basically reduces and matches the master's velocity at that point, 23.2 for master and slave at that point. And after that, since the execute ramp out or the ramp out command was given in this master cycle, the very next master cycle you come across the function block basically makes the slave axis or the knife axis ramp out, and that ramp out process is also smooth. It goes from whatever velocity you were at when you were speed matching to 0 velocity in a smooth process. So the advantage of this solution package is that given the parameters of your rotary knife, we generate 3 different cam profiles that are blended together: the ramp in, running, and ramp out. And the user really does not have to do anything to create or worry about these 3 cams or synchronizing these 3 cams and firing one cam to the other. All these are done automatically within this rotary knife function block, and you can see the output here. Here is an example where multiple parts were being processed continuously, and there were 4 knives in the system. You can see the 4 knives. Each master cycle corresponds to one knife making its cut, and you can see here each knife is basically speed matching. And there are 4 knives in the 0 to 360 degree complete physical cycle of the rotary knife. The execute ramp in happens in this master cycle. The very next cycle, you can see that the slave has started moving. And in this example, you can see that the slave axis is accelerating to match the master's velocity, and then it decelerates because the part length is much longer than the circumference of the knife. Again, this is an expanded view of the previous slide. You can see that your ramp in profile or your velocity at ramp in is smooth, and it ramps in and matches the velocity. And after that, it basically continues its running cam profile until the ramp out command is given. Now, a lot of you who've used the cam functionality with the MPIC controllers have used cam generator, have used the cam tool probably. For those of you who've used the standard MP product for a long time, the cam tool provides an easy way in which you can view the cams that you generate. And tangent matching is a popular curve type that has been used by people who use cams a lot. Just because you can match, basically because it provides a way of smoothly matching a straight line to a straight line, or speed matching areas can be matched using a smooth profile. However, there is one drawback for the tangent matching profile. I shouldn't call it a drawback. It's basically a characteristic of the tangent matching profile equation, is that if your straight lines that you want to match tangents along are such that they have a wide difference between these, or if their slopes are such that the slopes do not intersect or the slopes have are far apart, then you basically end up with a situation where the profile generated using the tangent matching can reverse in position. This would mean that the cam would reverse in velocity, or it would go one way and then the other, and then would have to reverse again to match the position. And this typically happens if your part length is much greater than the circumference of the knife. In this case, you might see that the knife has to go forward, reverse, and then forward again, just so that all the distance that it has to cover is covered in that time frame. This may not be an optimal solution for systems which have multiple knives, because you do not want to make wrong cuts when the speed need not be matched. And here's an example where we experimented with the tangent match profile, and when the part length was way longer than the knife circumference, you can see that the position reversed, and that can be seen from the velocity plot as well. The velocity is positive all along, and then it goes negative. There is no discontinuity in the profile. However, the profile goes into the negative area. The velocity basically goes in the negative area, which means a reversal in position for the knife before it continues on forward, and that continues because that's the shape of the cam that is generated. To prevent that from happening, we experimented with a Bezier curve to prevent the speed from reversing, or the position from reversing, or speed from going negative. And you can see here one extreme case in which the tangent matching was used, and you can see that the tangent matching basically reverses in a position, but with the same parameters on a Bezier curve. The red line shows how the velocity basically gets constrained, and the position does not reverse in this case. So we have made use of that Bezier curve and included that as an input in the rotary knife cam generation function block. So there is a bit input on the function block with which you can choose whether you want a reversible or a non-reversible cam. And if you choose a non-reversible cam, you end up using a Bezier curve to match the tangent positions between the two profiles. And here's an example of the same system that was shown 2 slides ago, where the position was reversing, and you can see that with the Bezier instead of the tangent matching profile, the position does not get reversed. Here's a comparison of using the tangent matching and Bezier curve for the same part length. And remember, this happens only when the part length is much greater than the knife diameter. This may not be a practical problem in a lot of applications, but there are applications we've seen where this can happen. And you can see here, if the part length is large, the knife position can reverse if tangent matching is used. It does not reverse when Bezier curve is used. And the speed going negative is prevented by using the Bezier curve. So that is an option that users can choose, and users should be aware of. Here's a sample application. Like I said before, the rotary knife does not mean that you can use it only for applications that involve knives or cutting. It can be used for applications that require placing or picking. Knives definitely for certain, but any kind of stamping application or like I said, placing application, you could use this function block and get a solution out of it. Next, we are going to talk about rotary knife with registration. Let me take a quick break here just to see if I can find any, if there are any questions that I can answer. Does the Bezier function slow down the throughput? No, the Bezier function does not slow down the throughput. The Bezier function is just a different equation in generating your cam profile. So it does not by any means slow down the master or slow down the slave or do anything, any kind of motion. It does not affect motion really, except that it prevents your running cam or your ramp in or your ramp out cams from going backwards or reversing in direction. It does not slow down the rate at which your production goes on. Does the Bezier curve limit homing to one direction only? The Bezier curve does not have anything to do with homing per se. You can decide your own homing procedure. These solution function blocks do not provide a solution for homing. The user will have to decide on the homing procedure by themselves. They basically will have to put a sensor or look at the absolute position of the knife and decide the shortest distance to go to a home position. The curve is essentially used for camming purposes only, and that's used for once you have parts and once you're trying to process parts is when the curve is being used. So it does not really constrain your motion before the camming has been done and before production has begun. There is a comment which says, on the function block you showed an option for allowing the blade to reverse in position. When would you want that to happen? There are applications when you may have a large load, or if your knife has a very large inertia, you might not want the application or the knife to stop, or you might want the knife to basically go forward and then reverse in position so that the inertia can be slowed down. If you have a very large inertia for the knife, you may want that reversing in direction to happen. You might not want to stop it, or because of the higher torque requirements that the Bezier curve may produce in such situations, you might want the whole knife to go forward and then come back and then do the cutting application. So it's more application dependent. If you do not have enough torque in your motor to decelerate and bring down the velocity to zero, you might want to keep the reversing tangent matching profile in there. Well, there are a few more questions that came in, but I would like to, just to save time, I'd like to continue on with the rotary knife with registration part of the solution, and then I'll try to answer the questions at the end of the webinar, or I can email the email answers to the people asking the questions. So again, the rotary knife with registration, there are basically two kinds. The first one is where you have nominal parts, but you have to make very small corrections, either positive or negative corrections, based on the part length that is being measured using the sensor. So although you've been given a theoretical part length, the part length may vary based on manufacturing processes, and you might have to make corrections for that. In such applications, there is a sensor that is placed upstream that senses and detects registration marks on the parts as they come through, as shown here. And the other kind of application is where you may have random parts that are coming at unknown intervals. So there is no uniform part length, or there is no, you may have to make large changes or small or large corrections, but the amount of corrections, it's basically the interval at which your parts are coming is going to be unknown. That's the second kind of rotary knife application which you may encounter. Now, this part of the solution uses the product buffer function block from the PLC Open toolbox that a lot of you might have used and are familiar with. The product buffer essentially is a rotary buffer that keeps track of the position of the master as the sensor detects it. So one of the first elements a user has to keep in mind, or user has to define when you deal with the rotary knife with registration, is the registration data, or basically they'll have to give the controller or give the project some information about their product buffer. And important terms to input to the function block or input into the application are the size of the buffer, the lockout distance, which is essentially the distance or the smallest distance between two parts. You don't want the product buffer to capture any noisy signals, and you basically set this lockout distance to tell the controller that any sensor input detected within the lockout distance can be ignored. So the product buffer will not look at such signals. That is this lockout distance variable. Sensor distance is the distance from the sensor to where the cut takes place, or where the processing takes place. The product away distance, it's the distance from the sensor to where the product can be considered to be processed and out of the way. That is kind of critical. Users should not ignore this distance, should not set it to default, or should not ignore this distance. This is kind of important, and we'll see why later. It essentially is used to update the use pointer variable inside the product buffer. So that is important. And then last but not least, you have to define which input, physical input, the sensor is wired into. And all this variable that we have declared are of data type product buffer struct. It's part of the registration data input on the product buffer function block. The other piece of information that the user will have to provide is something called a control data that will be used in this kind of application. And here again, mode is 1 for a rotary knife. The decision position is basically the position where a decision to cam out has to be made. If there are no more parts in the buffer and a decision to cam out has to be made, this is the position which on the master, which basically decides or tells the controller when to cam out or when to ramp out and go back to home position. The end sync position and start sync position are the positions where the synchronization should start. So this is the start sync position right here, and this is the end sync position, and those are on the master cycle. The safe engage distance is a distance where the cam can be engaged safely with a ramp in profile, and typically suggested in safe engage distance is 1 to 2 part lengths lesser than the sensor distance. So you can see here that if you engage the cam at somewhere in this area between the sensor and 1 product length, then you have the capability for the ramp in to take place successfully. If you try to engage the whole process here, you won't have enough time for the ramp in to take place. So you basically want to set your safe engage distance 1 or 2 part lengths less than your sensor distance. So sensor distance minus 1.25 part length would set me right here. So it's basically telling me that my cam in or the whole cam in process can start somewhere in this region, and that'll allow for my ramp in to take place in this particular master cycle, so I can get my first cut at that correct position. All this data is of data type, belongs to data type cam sync struct. And like I mentioned before, a user has to be careful in some of these parameters when they are using registration, just to ensure that the cam out decision is made properly, and they have to knowingly set these parameters based on the application. So the first thing to understand is if you're continuing your running cam, and if you're not ramping out, let's say your product buffer is full and there's parts coming in continuously, you basically continue your running cam and it continues like this. Let's say at a certain point your product buffer is empty and there are no more parts coming through. You will have to make a decision after the last part or just before the last part. You basically will have to do a ramp out. So in order to do a ramp out for the slave to go back to its home position, or its in a one knife system, let's say you want to bring the knife back to a 180-degree position where the knife is sitting at the top dead center. If you want it to ramp out, you will have to understand that the ramp out process is done automatically by the rotary knife function block, but the ramp out process takes place only when the master is past the decision position and the use pointer is equal to the store pointer. So in order to do that, we have to make sure that the decision position is defined correctly. I mentioned earlier that that decision position has to be defined correctly. And that is something that the user has to define properly. So in this case, if I choose my decision position to be somewhere here in the master cycle, and let's say my product away distance is also somewhere over here in the whole process, then these two, if these conditions basically are satisfied, I get my ramp out command from the from the inside the function block, and I will be able to ramp out. But also another thing to keep in mind is the blend data, the switchover position for going from the running cam to the ramp out cam will also have to be set such that the ramp out cam starts here, so that I can basically go and ramp out and go into the end cam. If the ramp out cam were starting at this location, then my ramp out would have waited for one more cycle to get executed, because once it passes that window, it basically gets executed only in the next cycle. So in this scenario here, I had to make sure that my blend position or blend out ramp out blend position was after the ramp out command was generated inside the function block. And to determine or to control that, I basically had to make sure my decision position and my product away distance fell within this window so I could ramp out immediately. So this was the last part that it processed, and after that last part, my cam or my knife basically ramped out and went to the home position. So in summary, here is a view of the rotary knife with registration function block. The various inputs into this function block are the product or the product buffer struct that takes care of all the product buffer information, the products that are captured by the sensor. The cam control data is of type cam sync struct, which contains all the information about when to cam out, when the window comes in, and so on. The blend data and the knife parameter variables are from the cam generator, the rotary knife cam generator. And then there's enabling and there's a stop buffering if you want to temporarily pause the knife by flushing out parts in the buffer. You can also do that here. The outputs are the regular PLC open outputs, along with a current buffer level and the number of items processed in this for this function block. One thing to note, a difference between the regular rotary knife without registration and the rotary knife with registration is that this function block, the one with registration, basically decides when to ramp in and when to ramp out based on the number of products in the buffer and the distance that the master has traveled. The other rotary knife, the one that does not use registration inputs, the user has to determine when to engage the knife and when to disengage the knife, because it's not based on any sensory input. Here's a quick here's a view of the logic analyzer showing master position and slave position and some of the pointers in the product buffer function block. And this is for a random rotary knife where the parts were coming in at random, and you can see that as soon as the store pointer started getting positions, we do the initial shift and then a ramp in happens, and then there's a short part, a medium length part, and then another part, and so on. So this is and the shifting is basically done away or in between when the sync speed sync zone happens, so that it's using all the time that it can to do the shift to make it as smooth as possible. In summary, in order to implement the rotary knife template, we basically it's fairly simple. You have to place the rotary knife cam generator function block in a slow task. This is just because this is generating 3 cam tables, and you want to give it enough time for it to generate its cam table, and this can be done by the user. You can once you're done with a part length, you can basically go in and change it and refire the execute. It'll come out with 3 different cam profiles for your new part length. Once you're done with that, you have to home the rotary knife based on the number of knives, as we discussed earlier. Home positions for the various knife configurations that we tested out are shown here. You could probably use it for a larger number of knives if they're symmetric, but in our experience, we've not seen applications with more than 4 knives. So these are the home positions for configurations that have up to 4 knives. Once they're homed, you essentially can run either the rotary knife or the rotary knife with registration function blocks. Either or, you don't have to use both or at the same time. If you're using the rotary knife without registration, the user has to determine the logic for ramping in and ramping out. If you have sensors and have registration, the user will have to specify registration data information, control data information, and some elements of blend data if you want it to be different from the default. So in summary, the whole template basically consists of 3 different function blocks, the rotary knife cam generator and two rotary knife function blocks, one with registration and one without registration. All these function blocks essentially use functions that are part of the CAM toolbox and the PLC Open toolbox. It uses, for example, CAM generator, CAM table manager, CAM control, CAM blend, CAM shift control from the CAM toolbox, and a product buffer for part registration from the PLC Open toolbox. And that is all I have as part of presentation. I will try to take a look at your questions and try to answer them one by one. There is a question: if you're using the Express version of programming software, can we have both function blocks in the same? Having both function blocks in the same task, will it hurt us? Yes. This is basically the reason why we split it up into 2 different tasks, at least 2 different tasks, is because we want the CAM generation to happen in a slow task, and the control of the rotary knife to happen in a fast task, so that if it needs to make quick shifts or quick corrections, you basically want your processor to run at a fast rate. Now, it is not required that you should use the CAM generator, rotary knife CAM generator function block that we talked about, because that's the one that takes more time. So let's say the user has predefined CAM tables that can be created and can be stored in the controller, then they do not have to use that CAM generator function block and use it in a slow task. If there is any other way of generating the data in a medium or fast task, then they can use that data. You're not tied to using the rotary knife CAM generator function block. It's the rotary knife CAM generator function block that requires a slow task. So if you're an Express and you can find out if you can get the CAM data in an easy way with which you can run the one task at fast rates, then you can do it. It's not going to hurt you in that case. But generally, if you are leaving the CAM generation to be taken care of by the controller, you want to run that particular function block, the rotary knife CAM generator function block, in a slow task. In the Bezier curve, the acceleration is increased to compensate. That is correct. The Bezier curve has a drawback in which you basically will have to size your application. So if you don't want it to reverse, you basically have to. It's like braking hard. So you have to size the application properly. Will the template tell you whether your profile is impossible due to rotating inertia? No, this template is not going to warn or tell you about the torque or tell you about any inertia calculations. This is assuming that all the calculations for inertia and sizing the motor have been done previously. So this takes care of only sending control signals or taking care of the application for controlling the application. It does not take care of sizing or analysis of the inertia of the load. How do we get this? Will it be in the CAM Toolbox user library? At present, we plan to keep this as a template. So this will be released in on the Yaskawa website as a template, which the users can basically import as a user library, or they can basically use this after downloading it. They could use this project itself and fill in your other logic to complete your application. So initially we intended to be a template for anybody who wants to download it. Will the presentation be emailed to the attendees? The presentation is going to be is being recorded, so it will be available on our training website. So you should be able to log in and get the presentation. It'll take a few days though. If there are no more questions, I'd like to end this webinar. Thank you everybody for attending. If you have any questions, please feel free to email me. My name is Nishant, and if you do not get my email address, you could email our training department, and they can forward questions or emails to me so that I can get back to you. Thank you.